next topic is an exercise which someone asked me about last exercise hour, and the problem was the following. Was if you have a parallel plate capacitor. Let's see, like this. In the problem it's infinitely large, so there's no problem with the edges. So let's just look at, let's say, 1 square meter of it to get the physics of, well, what happens per unit interface, unit area. Let's see, x3 hat. The E field is simply x3 hat, and then E3, which is some constant, okay? And now the question is, if there is a charge distribution sigma, I mean a surface charge sigma on the top and the bottom, let's see, plus sigma and minus sigma on the top and the bottom plate. There's a constant electrical field. Now what is the force on these plates from the electromagnetic field? And try to calculate these from the Maxwell stress tensor. Okay? Use this, and the problem also said to use one specific formula, which was the following: that the force is equal to the following. There's one term which is related to the stress tensor, integrating over a surface. We went through this on a previous lecture, so I won't go through the details. And then there's one term which is basically the this is the flow of momentum, and this is the density of momentum, right? So if there's a force, it comes from some sort of change in this balance. Okay, now to get the Maxwell stress tensor is easy because the formula is given. Tij is equal to epsilon naught Ei Ej minus a half delta Ij E square. And you know what the E field is. It's simply a constant. So there's only, let's see, there's only one surviving, no, there's only going to be something on the diagonal of the stress tensor. And if you insert into the formula, this is straightforward, and I don't think any of you will have problems if you just insert into the formula without thinking. It should work just fine. But the second question was calculate the momentum flow. So there's a force on this plate, right? There's a force on this plate. Because they have opposite charge, so they'll try to attract each other. That's pretty obvious. Now, how do you calculate the momentum flow? Is there a momentum flow? Because there's no H field. So we know that the momentum density, which is proportional to the Poynting's vector, is proportional to E cross H. Okay, but there's no momentum density anywhere because there's no magnetic field anywhere. So where is there a momentum flow is the question. And if there is one, why is there one? So I suggest that you discuss for 2 minutes with your next neighbor and try to figure this out. And if you can't, I will show you how to do it on the blackboard. Is the momentum flow 0? Yes, no question. Take the chance. Well, anyone take a guess and then say why. It's not a simple, it's not obvious. It's okay to be wrong. He says no, there's no momentum flow because there's no magnetic field and there's no momentum density anywhere. Right. Sorry. You were wrong. That's okay. And you have to think a bit about this, right? But remember the following. If you have a force, you can write it as the time derivative of the momentum. Right? If I'm pushing my car, let's say, on a flat surface, and it gains momentum as I push it, well, my force is equal to the time derivative of the momentum the car gets. And it's the same thing here. There is a force, so there has to be a momentum flow. And I think this is best illustrated by a story about cats. A friend of mine came to visit me when I was a student, and I lived not very far from here in a house where the people owning the house lived in the first floor, and we lived in the second floor, and they had 2 crazy cats. So when he shows up and rings the doorbell, I open the door, and one cat runs in, and the other one runs out at exactly the same time. And this friend of mine has some sort of fluid mechanics course this semester. So he notes that, wow, that's the first time I've seen 0 net flux of cats. And it's exactly the same thing here, right? Because there's some force, electric force, on the 2 parallel plates. But why don't they move? Why don't they move? Why don't they gain momentum? Anyone? Well, if I push this table and with a force and it doesn't move, why not? Why doesn't it move when I push it? Yeah. It says that I'm too weak, and that's possibly true. I could try a bit harder. Well, yeah, it looks like I'm too weak, but let's put it on a more mathematical footing, let's say. Why doesn't it move? Yeah, there's another force stopping it, right? So when I say that there's a constant distance here, that means that something has to hold that distance. There has to be either a dielectric in between, or there has to be some bolts on the plates saying that they have to be still. So this means that there's flow on momentum, there's electromagnetic flow on momentum, but there's also an equal opposite mechanical momentum. So there's an electrical cat and a mechanical cat, and when they pass the door at the same time, there's no net flux of cats. So as you can see here, we have 2 terms in the force. This is the term that you were instinctively thinking of. But there's also this term. There's not only the, let's say, the radiation stuff, but there's also the, let's say, constant electrostatic or magnetostatic forces. They do exist, right? You have electrostatic and magnetostatic forces. And because force is equal to the change in momentum, well, then there must be a flux in momentum. It's just that the mechanical momentum balances it. So in fact, to find this momentum is not very hard, because T is exactly the momentum flux. So let's say that T set z, that's one of the surviving components. Yeah. This means momentum flux in the z direction of a z component momentum, right? Meaning that there is indeed an electrostatic force on the plates. Yeah, I think we've come to a conclusion here. Is this clear for everyone? You understand a bit more about the Maxwell stress tensor now, I hope? Anything that's unclear? Okay, we continue 10 past with guided waves.